So this is the second PowerPoint on probability. The first video covers the first half of the unit, and then this will cover the second half. That's why it's probability 2. You'll notice the nice word art that is red, white, and blue, very patriotic. So you can see this here, very patriotic word art. Yes, that's how I did all of my projects in high school. I would put word art as the title, and it always got me 100. So. Nope, there we go. So probability, why is it doing that? That's so weird. Probability of an event, it's going to be denoted by P and then the parentheses of the event, where you're taking the number of successes divided by the total outcome. So probability will always be a decimal, whereas in the last unit, or I guess the last section, we talked about counting problems. Those will always be big numbers. So like, how many ways can you do this? How many ways can you arrange your schedule? How many different types of social security numbers can you have? Those will be big numbers. Probability is always going to be a decimal. It's going to be a number between 0 and 1. And the method for calculating probabilities is only appropriate when the outcomes of the sample space are equally likely. Experimental probability is when you actually conduct an experiment and you are recording the outcome. So it's the relative frequency, which means the decimal, at which a chance experiment occurs. So if you flip a fair coin 30 times and get 17 heads, your experimental probability would be 17 out of 30. However, if you actually were thinking about, and this will be the next term that we learn is theoretical probability, you would expect to get 15 out of 30. So this is not necessarily what you would expect to happen. It's greater than what you would expect. But this is when you conduct the experiment. This is the experimental probability. So what you actually got versus what you would expect to happen. And so what we would expect to happen is going to be what we call theoretical probability. The next thing, we've kind of talked about this a little bit, is the law of large numbers. And so essentially what that means is if I kept flipping coins over and over and over and over, and maybe, for instance, if I had it 30 times, if I kept flipping coins 100 times, I would get closer and closer to the theoretical probability. So if you flip a coin twice and you get 0 out of 2 tails, then you would say there's a 0% chance of getting tails, which isn't accurate. That's why if you keep flipping your coin over and over and over and over, it's going to approach what we call the theoretical or the true probability. So in other words, large numbers, if I keep increasing my trials, so if I increase trials, then that's going to approach, my experimental probability will approach what the true probability is. So basic rules of probability, you do have to memorize these. The first one is that a probability is any number between 0 and 1 inclusive. So it could be a 0% chance, could be a 100% chance. The second rule is that if S is your sample space, and remember, sample space is all of the possible outcomes. So for instance, a sample space of flipping a coin, you have heads and you have tails. So my sample space would be heads and tails. So the probability of landing or flipping a heads or a tails is 100%, always. So 100% is your sample space. The next rule is the complement rule. Remember, complement, like if you have event E, then its complement is E to the C power, and we use this symbol to represent complement. So if I calculate the probability of E plus the probability of E complement, or not E, it will be 100%. So for instance, if my event were the probability of rolling the dice, like the probability of rolling a 1 would be 1 out of 6, because I have a 1 in 6 chance of rolling a 1. The probability of not rolling a 1 would be 2, 3, 4, 5, and 6, which would be 5 out of 6. And that adds up to 6 out of 6, which is 1. So probability of rolling a 6 or rolling a 1, probability of not rolling a 1, add those together, you get 100%. So there's a 100% chance of either rolling a 1 or not rolling a 1. An independent event, so two events are independent if knowing that one will occur does not change the probability of the others occurring. So an example could be a randomly selected student is female. What is the probability that she plays soccer? They're independent events because being female and being soccer, the probability does not change. A randomly selected student is female. What is the probability that she plays football? Well, there would be no female football players, so that would be a dependent event. One thing, though, that I think is more important to understand is saying that the probability does not change. Anytime that you see the word replacement, that would mean that it is independent, so replacement. So for instance, if I am drawing cards or drawing marbles or those are usually the only two that I see, like drawing cards, drawing marbles out of a hat. If I say with replacement, then that means that every single time, if I'm replacing that marble every time, I'm replacing the card every time, my probability is staying the same. So think about, does my probability stay the same with each trial, or is it changing? If it changes, then you would say that the events are dependent. So there are rules for multiplication. If you have independent events, in order to find their intersection, so in order to find their intersection, you take the probability of A times the probability of B. So let's say that the example was, what is the probability of drawing two clubs and with replacement? So if I said probability of drawing two clubs in a row. If it's with replacement, then the chance of drawing one club is 1/4. I replace it times 1/4. So you get 1/16. So I have a 1 in 16 chance of drawing two clubs in a row. If I said, what is the probability of drawing two clubs without replacement, meaning I draw one club and now I have one less card and I also have one less club. So the probability of drawing one club is 1/4, or you could say 13 out of 52. Doesn't matter, but I'm going to use 13 out of 52 to show you how the next one would work. So I've taken one club away and I've also taken one card away. So what this stands for, what this means is the probability of B given A. So given that A has already occurred, so given I've taken one club away, I have now, my new probability now is 12 out of 51. So I would take 13 out of 52 times 12 out of 51. And all that happened is I decreased the numerator and denominator by 1 because now I no longer have a club and I no longer have that card. So each thing gets decreased by 1. That would be a general rule. This would be for dependent events. So for independent, you're multiplying them together. For dependent, you're also multiplying them together, but you have to think about with respect to the event that's already occurred. So probability of A and B, remember that's the intersection. What does this mean? So in order to solve for that, if they're independent, you just multiply them together. A times B. So if I said, like the example of two clubs with replacement, I would take 1/4 times 1/4. So that's the probability of getting a club and two clubs in a row. So here's an example. It says a certain brand of light bulbs are defective 5% of the time. You randomly pick a package of two such that bulbs off the shelf of a store. What is the probability that both bulbs are defective? So can you assume that they are independent? I guess you can't talk back to me, but you can, because one bulb does not affect the defectiveness of another bulb. So in order to find the probability of taking two light bulbs off of a shelf and they are both defective, I would take 5% times 5%. So there is a 0.0025 or 0.25% chance of having 2 light bulbs that are defective in a package. If they are not independent, then you use the probability of A times the probability of B given A. There's not some like fancy formula for that other than thinking through it logically. Like so there are 7 girls and 8 boys in a math class. The teacher selects 2 at random to answer questions on the board. What is the probability that both students are girls? Are these events independent? So I start out with, I have 7 girls out of 15 total people. They are not independent because I'm not replacing the girl. Once I've chosen her, she's already gone. So she gets chosen. Now I am left with 6 girls and I only have 14 people. So a lot of times you're decreasing the numerator and the denominator. If the question said, because I've seen examples where it said, like, what is the probability that you choose 1 girl and then 1 boy? So in that case, it would be 7 out of, and it would need to say 1 girl, then 1 boy, because the order would matter for that. So 1 girl, then 1 boy. It would be 7 out of 15 times. Then I have 8 boys, but only 14 people left. And that would be for this example. So my denominator is decreasing by 1, but my numerator didn't change because I have all of my boys still to choose from. So you have to think, that's why sometimes the probability unit is a little difficult, because you have to think about the actual scenario, and there's no possible way to give you every type of question. We just give you the tools that you need to answer every type of question. So understanding the concepts and the foundation is important, but knowing how to apply it to all situations is what's going to be the most crucial thing for this test. So in this example, both are girls. You have 7 girls, then you have 6 girls. If I did one that said 1 girl, then 1 boy, this is the probability of choosing a girl. Okay, 1 girl is gone, but I still have 8 boys left, but I only have 14 people, so that's why this changed right here. And then you end up getting 20%. Suppose I will pick 2 cards from a standard deck without replacement. What is the probability that I pick 2 spades? So that's kind of like the one that we talked about earlier. So the probability of 1 spade is 13 out of 52. Or 1/4. Then I take 1 away, and I also have 1 less card. So I only have 12 spades left, and I only have 51 cards left. And then when you multiply that out, you get 1 out of 17. Now I would probably prefer, you could do it written as a fraction or a decimal. I'm not going to be picky about which one is which, but I think I typically always do decimals. Does not matter though. So hear me when I say it does not matter if you do decimals or fractions. And so that's the probability of getting a spade given that a spade has already been drawn. So that's what that vertical line, like I read that as B given A. That vertical line means given. So given that I drew 1 spade, the probability of drawing another spade means I have 12 left out of 51 total cards. The next rule is the addition rule. So if 2 events are disjoint, another word for that is mutually exclusive. So if 2 events are disjoint or mutually exclusive, then the probability of E or F, you just add those 2 together. And they never occur at the same time. So this formula right here, so if 2 events are not disjoint, meaning they do happen at the same time, this is the formula that you use. It is on the formula chart. So you don't have to memorize it. But for an OR equation, you add E plus F, and then you subtract the intersection. And let me explain kind of why we do that. So imagine I have a Venn diagram that looks like this. You told me yesterday or 2 days ago that when you shade a Venn diagram, if this is E and this is F, E or F indicates that I'm shading all of E and I'm shading all of F, Let me get a different color. And I'm shading all of F. So I'm adding all of E and I'm adding all of F, but you'll notice, and you can see in this cross stitching right here, that I have shaded the intersection twice. So I need to erase one of those. I need to erase one of those so that it only gets counted twice, only gets counted once. So if I erase or if I subtract one of the intersections, I'm only left with one left. That's kind of like a visual of what we're doing here. This formula right here is the same thing as this, but an intersection for mutually exclusive events is just 0 because the probability of E and F occurring when they're mutually exclusive is 0. That means that your Venn diagram looks something like this. Means that they never happen at the same time. So there is no intersection. There will be I've seen several multiple choice questions that have tried to trick people into saying, like, what is the intersection of this mutually exclusive event? The intersection of a mutually exclusive event is 0. So the probability of E and F equals 0 for mutually exclusive events. So what does this mean? If they're mutually exclusive, yes, you add them together. There is no intersection. So we have a large auto center that sells cars made by different manufacturers. 3 of these are Honda, Nissan, and Toyota. These are not simple events since there are many types of each brand. So then it gives us the probability of each. Now, if you're going to buy one car, then you can't buy a Honda, a Nissan, and a Toyota at the same time. So these are disjoint because if you're only going to buy one car, you're going to buy one of the 3. So the probability of buying a Honda or a Nissan or a Toyota, I'm just going to add up the probabilities. So there's a 57% chance of buying at least one of the 3. So then the probability of that complement, like not buying a Honda or a Nissan or a Toyota, would be just 1 minus that. 43%, because you either buy one of those 3 cars or you don't, and that adds up to 100%. So if they're not mutually exclusive, remember that you have to subtract the intersection. So here it is again. This example, it says musical styles other than rock and pop are becoming more popular. A survey of college students finds that the probability they like country music is 40%. Probability that they like jazz is 30, and the probability that they like both is 10. What is the probability that they like country or jazz? So you would take the probability of country plus the probability of jazz minus the probability of country and jazz. So you would take 0.4 plus 0.3 minus 0.1, which gives you 0.6. If they are independent, so if you have independent events, they're not going to give you the intersection. They're going to assume that you know how to calculate it. Then you just multiply them together. So if they are independent, then your intersection is just the 2 events multiplied together. If they are mutually exclusive, then it equals 0. This is something that often gets confused, and I've seen it every year that I've taught. Mutually exclusive and independent are not the same. They are not the same thing. Mutually exclusive automatically means that they are dependent events. So mutually exclusive events are dependent. And independent events are not mutually exclusive. So sometimes people get those confused. They are not the same thing. In fact, they are quite the opposite. Mutually exclusive events are always dependent, because if one happens, that depends on the other not happening. Independent events are not mutually exclusive. They are not. They will have an intersection and they will happen at the same time. And the way that we find that is by multiplying those together. So here's an example, and this is what I see a lot on the AP test and just quizzes and tests in general. It gives me A and B and it tells me that they're independent, and I want to find A or B. So I'm going to use the formula that's on the formula chart. Probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. And I have to actually solve for this probability because they didn't give it to me. And so solving for that, it is 0.45 times 0.35. So then I get 0.45 plus 0.35 minus their intersection. And you end up getting, oh, there we go. So if A and B are disjoint, are they independent? Disjoint events do not happen at the same time. So if A occurs, can B occur? No. Disjoint events are dependent. So that's just saying that again. And so you end up getting 0.6425. If a coin is flipped and a die is rolled at the same time, what is the probability that you will get a tail or a number less than 3? So I want to find the probability of, tail or less than 3. So I need to find the probability of getting a tail plus the probability of getting less than 3 minus the probability of tail and less than 3. I guess I could use I think I used the wrong symbol here. This should be a U, and then this should be an and. There we go. So probability of getting a tail is 1/2. The probability of getting a number less than 3 when you're rolling a die is 2 out of 6, or 1/3. Because it's just less than 3, not less than or equal to. So your options are 1 and 2. Minus, now are these events independent? Like the probability of flipping a coin and the probability of rolling a die, those do not depend on each other. The probabilities don't change ever. So in order to find their intersection, I'm just going to multiply them together. So 1/2 times 1/3. So you get 1/2 plus 1/3 minus 1/6. And you get, let's see, probably need a calculator. You get 4/6, which reduces to 2/3. Let's see what the PowerPoint says. Oh, it's giving all the sample spaces. I just did that in a different way. So this is showing it in a Venn diagram. Coin is tails, roll is less than 3. And you're reading this as like heads and a 1, heads and a 2, heads and 3, heads and 4. So you have 12 different options. And then in the left, all the tails. On the right, all the heads, less than 3. And then in the middle, there's 2 events where you're getting tails and less than 1. So flipping a coin and rolling a die are independent. Independence also implies the events are not disjoint, hence the overlap. So you only count T1 and T2 once. And that's how I did it mathematically. Another way, if you wanted to read the Venn diagram, you would count all of these, all of these, all of these. These would get excluded because the shaded area would be all of this. But I think that doing it mathematically is easier for me. If you think the other way, then that's fine. Either way that you find it, if you get the same outcome, I'm only checking the answer. The next one is, so it says a certain brand of light bulbs are defective 5% of the time. You randomly pick a package of 2. What is the probability that exactly 1 is defective? So with this, you have 2 options. So you have light bulb 1 and you have light bulb 2. So you could either get defective, not defective. That should be a D. Or you could get not defective and then defective. And so I need to add both of those outcomes together because there's 2 scenarios of getting exactly 1 that is defective. So I need to add those scenarios up. So this first scenario, since they're independent, it's like saying defective, which is 0.05, and not defective is 0.95. So defective times not defective. Plus, the second scenario is my first light bulb is not defective, so 0.95 times 0.05, which would be not defective and defective. And then if you add those two together, you'll get your total answer. They wrote it as defective and defective complement. So there is a 0.095% or 0.095 chance or a 9.5% chance of getting exactly one that is defective. So when you see the word exactly one, you just have to think of all, so you're going to add all possible scenarios. So if you're adding all the possible scenarios, like let's say if there were three light bulbs that I were choosing from, you have defective, not defective, not defective, plus not defective, defective, not defective, plus N and D. So you would be adding 3 scenarios together. And if you had 4, then you would do that as well. You would just keep adding. So when it says exactly 1, you're going to add all of the possible scenarios together. This next example, so light bulbs defective 5% of the time. You randomly pick a package of 2. What is the probability at least 1 is defective? At least 1. This is another, so you have exactly 1 where you're adding all the possible scenarios. At least, anytime you see at least 1, the formula for that, and you do have to memorize, is 1 minus the probability of none. So in this specific context, so if you have at least 1, that means that 100% of the time, you're either going to have at least 1 or you're going to have none. Okay, so the only possible scenario where you don't have at least 1 light bulb that is defective is when none of the light bulbs are defective. So that's why I subtract it from 100%, because the only scenario that doesn't include 1 defective light bulb is when none of the light bulbs are defective. So to find the probability that none of the light bulbs are defective would be 0.95 times 0.95. That would mean the first light bulb is defective and or not defective, the second light bulb is not defective. And you end up getting 0.0975. Here's the rule right here. So at least 1 equals 1 minus the probability of none. There we go. So I just showed you the rule early. I was looking at this. I want you to ignore this. This is like the long way to do it. So cross that out of your notes. This is the way that I showed you on the example. And you end up getting the same answer, whichever way they did it. For a sales promotion, the manufacturer places winning symbols under the caps of 10% of all Dr. Pepper bottles. You buy a 6-pack. What is the probability that you win something? So that means that you get at least 1 out of 6 Dr. Pepper bottles that has a prize. So you want to do 1 minus the probability that none of the Dr. Pepper bottles have a prize in it. So in this case, so 1 minus the probability that no prizes. So in this case, if I have 6 Dr. Pepper cans and there's a 10% chance of winning, that means that there's a 90% chance that it does not have a prize. Each bottle is going to have a 90% chance of not getting a prize, and they'll all be independent of each other. So that means I'm going to take 0.9 to the 6th power, or 0.9 times 0.9 times 0.9, 6 times. And when you solve that, you end up getting 0.4686. Okay, the last rule for this is conditional probability. That means that a probability that takes into account a given condition. So you'll use conditional probability when you see the word if or you see the word given. So, like, what is the probability that they made an A on the test given that they studied for at least 2 hours? And so if you see these words, you know that you're going to be using a conditional probability. This formula is given to you on the formula chart, so you don't have to memorize. So the two formulas that they give you is the A or B formula, which is the A plus B minus A and B. This should be a U. I keep mixing these up. This is not good. There we go. A or B. So they give you this formula, and then they give you this formula. So these are the two that you are given. If you want to get a formula chart out of the box in my room, then you can look at it as well. It's in the second column of the first page. And so basically what that means is the probability, you read that as the probability of A and B over just the probability of A. So given A has already occurred, or given that B has already occurred, what is the probability of A? So in this example, it says in a recent study, it was found that the probability that a randomly selected student is a girl is 51 and is a girl and plays sports is 10. If the student is female, what is the probability that she plays sports? So this is my intersection. So girl and sports is 0.1 and just a girl is 0.51. So the probability of, so if the student is a female, what is the probability that she plays sports? So sports given female. I guess we could say girl because I used the G in the other. I would take sports and girl over just girl. So that would be 0.10 over 0.51. So you're just plugging into a formula for these. You just kind of have to know what part you are plugging in for. And sometimes, like I've seen examples where they give you like these two parts and then you're solving for the intersection. Or they give you the conditional and they give you the intersection, but you're solving for like the probability of being a girl. So they'll always give you two pieces of the puzzle and you're solving for the third one using the formula. Same thing. The probability that a randomly selected student plays sports if they are male is 0.31. So here's where it works. So this is the conditional probability. So probability that they play sports given they're male is 0.31. What is the probability that the student is male and plays sports? So I am looking for male and sports if the probability that they are male is 0.49. So this is just male. So the formula is, if it's sports given male, is sports and male over just male. And I have this and I have this. So I would plug in 0.31 equals sports and male over 0.49. Then I multiply the two together and see what you end up getting. There we go. 0.1519. Mostly, so I've seen conditional probability is mostly in the form of two-way tables where they're asking questions based on that table. So for number 12, and this is what you mostly see on free responses for a probability question. So it says, what is the probability that the driver is a student? So I'm going to look at all of the students, total students, over total. So 195 over 359. So total students over total. And I would want you to write it as probability of student. Like that's the kind of notation I'm looking for on a free response. What is the probability that the driver drives a European car? Well, I'm going to look at the total European cars, put that over 359. Total. So you're always putting it over the total until we'll see an example with a conditional probability here in a minute. What is the probability that the driver is staff and drives an Asian car? So I'm going to look at the intersection of staff, Asian car, which is just the 47 out of the 359. So I'm looking at both because it says and. So and means intersection. The next one is American or Asian car. So if it's an or, then I'm going to look at the total American. So total of this or total of this, 102. Now, since it's talking about two types of cars, they never intersect, so I don't need to subtract the intersection. So I'm going to take 212 plus 102 over the total. Because those two events are mutually exclusive. You can't drive an American and an Asian car. So the answer is yes to this. Yes, it is disjoint. This one, it says driver is staff or drives an Asian car. So in this case, I'm going to look at the total staff, which is 164. And I'm going to look at the Asian car, which is the 102. So 164 plus 102. But if you notice, one number got counted twice. Got counted in the column and the row, which is this 47. So I need to subtract one of them away. And it's like the formula, like A plus B minus A and B. I'm subtracting the intersection because I counted it twice, all over 359. Another way that you could do it, if you don't want to add the totals and subtract the intersection, is saying 105 plus 12 plus 47 plus 55. Like I'm adding these four numbers together. And then you're only counting the 47 once. So there's two types of ways. This is the first type of way, second type of way. So adding the total, subtracting the intersection, or just adding up the numbers in the rows and columns. That way you're only counting it once. These are not disjoint. They can happen at the same time. Okay, the next one is a conditional. So if the driver is a student, what is the probability that they drive an American car? So you will, when you're doing these on a free response or on any problem, you're going to circle the if, driver is a student. So now I am only concerned with this column. The rest of it can just go away. So out of all of my students, the probability that they drive an American car is 107 out of 195, because this is out of the students. So out of the students, if they're a student, the probability that they drive an American car is 107 out of 195. So now you're not looking at the total, you're just looking at the total students, because it's giving me the good condition that they're a student. What is the probability that the driver is a student if the driver drives a European car? So if they drive a European car, so now I'm only isolating this row right here. So out of 45, the probability that they are a student is 33. So 33 out of 45. The last thing is a hypothetical 1000 table, and this is sometimes easy to build if you are answering a probability question, because it's an easy way to organize your thoughts. So you can use these tables, you have to create them yourself, to compute a probability of an intersection of two events and the probability of a union of two events. In many situations, you may only know the probability of some events, and then you have to solve for the other ones. So creating a hypothetical 1000 and using a table to compute is usually going to be the best way. And I'll go over this more with you next class too, because this I think just takes a little bit more practice. So here we have an example. It's the report, the TV drama and comedy viewers and health information. So L represents the event that a randomly selected American reports learning something new about a health issue from a TV show. And F is the random event that the adult is a female. So here's data from the survey. There's a 58% chance that they've learned something new in the past 6 months. So there's a 58% chance that they've learned something in the past 6 months. There's a 50% chance of being female. And the probability of both is 31%. So I have all this information, but I cannot answer every single type of problem that they're asking me for. So I want to create what we call a hypothetical 1000 table from that. So what I do is I begin by labeling the rows and columns of the table. So you've got female, so you have both of your events, female and learn from TV. And those go in the top left column and then the top row. And it's always a 2x2 table where you have female and then not female. You could write it as female complement, or not female, you can also write like this, not female, where this means not. I've seen it written like 3 different ways. I usually do this right here, the not female. And then learn from TV, didn't learn from TV. Whoops, not F, should be L. So then I'm going to fill in what I know. I know that 58% learned from TV. So I always put 1000 in my bottom right cell. So these are the totals of each column and row, and then out of 1000. And the reason why we use 1000 is because it goes out 3 decimal places whenever you end up solving it. So I'm going to go to total of learned from TV. So I'm going to put 580 in this row right here because that's how many people learned from TV. Then I have total females. That's going to be 500. Automatically, I can go ahead and fill in the other totals. So that would mean that not females would also be 500. And not learning from TV would be 420. And that I just got from filling in the complements of my events. The last piece of information they give me is the intersection of learn from TV and female. That's going to be 310. So there's a 31% chance, 310. From there, I can now fill in the rest of my events. So 500 minus 310 is 190. 580 minus 310 is 270, and then 230. Yes. So once you have this chart filled in, like the hardest part is filling in the chart. Once you have it filled in, you can answer any question that they may come at you with. You can answer anything that they may ask you. What's the probability of not being female and not learning from TV? Well, then you would answer 200 or 0.23. So you fill in all of the questions. It's giving you all the details. We did all that. We filled the rest in. So now here's a question. It says, what is the probability that a randomly selected adult American has learned something new about a health issue or disease from a TV show in the previous 6 months, or is a female? So it's asking me, learned something new or female. So I'm going to take all of the learned something new, and I'm going to take all of the females. So all of learned something new, all of females. So it's just adding, it's just adding these 3 together. All of learned something new, all of females, and then subtract the intersection 1 time. Or you're just adding these 3 together. Now, you could, I know that this seems like a lot of work because for this particular question, you could have just used the formula that is 0.58 plus 0.5 minus 0.31. But that wouldn't work for every single type of question. So Let me ask you a question where you may need to use the chart, or you may need to build the chart because you can't just come up with it offhand. So maybe the question says, what is the probability that they did not learn and are not female? So, and then there's an and. So they did not learn, so learn complement, and they're female complement. So they didn't learn and they're not female. It would be this right here, 230 out of 1,000. So that would be 0.23. And could you have come up with that without making a table? Yes. But it's easier for me to build a table. So we'll get lots of practice building the table. Okay, the next example, it says management has determined that a customer's returned 12% of the items assembled by inexperienced employees, whereas only 3% of the items assembled by experienced employees are returned. Due to turnover and absenteeism as an assembly plant, inexperienced employees assembled 20% of the items. Construct a tree diagram or a chart for this data. And what is the probability that an item is returned? Instead of making a tree diagram, I'm going to say let's make a hypothetical 1,000. So you have to think like, what are my two categories, or what are the two things that I'm looking at? So I'm looking at experienced and inexperienced. So they're either experienced or they're inexperienced, and then they're also returned or they're not returned. So when you're making your chart, you need two separate events. So here's my chart. Returned and not returned. Then I'm going to go back in a second. So it says that customers return 12% of the items by inexperienced employees. So from there, this is a hypothetical, I guess, 100. If you made it 2,000, then, or 1,000, then you would just add a 0. You would move the decimal place over for all of them. But you can do a hypothetical 1,000. That just means it goes out 2 decimal places. Okay, so when I'm looking at this, if I'm just using hypothetical 100, if you wanted to, I think that might trip some of you up. If I were to do 1,000, then what I would do is I would add a 0 here, 0, 0, and move all of these decimal places over. So this would be 24, 24, 48, 776, 176, 952. So I'm going to take before I can deal with the 12% and the 3% from the problem, the first thing I want to do is talk about the totals of experienced and inexperienced. So in the last sentence it says 20% of the employees are inexperienced. So I'm going to add in this 200 here, which means that 80% of the employees are experienced, 800. From there, it says that 12% of the total of inexperienced items, or I guess the items from inexperienced, are returned. So to get this 24, I'm going to take 12% of the total. So 0.12 times 200. That's how I got this 24. Because it's only 12% of the inexperienced. And then for experienced, the next thing they give me is that 3% of the experienced are returned. So 0.03 times 800 is how I get this 24. So you can fill in 24, 24, 800, 200. From there, then you can fill in the rest of the chart. So the 48, 776, 176, 952. Then it can ask you any question that you want. So what is the probability that an item is returned? I'm going to look at the total out of so 48 out of 1,000. And the next question says, if an item is returned, what is the probability that an inexperienced employee assembled it? So I'm going to look at just the returned. So out of 48, the probability that an inexperienced assembled it is 24 out of 48. Which equals 50%. or 0.5.